really cool to hear. And talking about that, today I went on your site on X, and I saw something the other day about a new material that you've got set up for DARPA. But today I saw the titanium diboride,
Yes.
and how that is going to be used in the SM39. Can you explain a little bit more about that? Because that's really fascinating.
Sure. Well, that's a metal ceramic. It incorporates elements of boron, and that's a high temperature material. It's a very high temperature titanium, and the density of that material is about the same as titanium. As a matter of fact, it's lower. So it has extraordinary mechanical properties. It doesn't it has a very low thermal coefficient of thermal expansion, so it doesn't expand very much at high temperatures.
Yeah.
And it's basically a high temperature, very stiff and resilient material. And as a consequence, you can have engines made out of this. You can have engine components. You can have airframes. And so if you're building an airplane for high speed out of a metal, that's really a great material to use. And so we've been looking at that for about a decade now, and pioneering a lot of the manufacturing techniques to make that in large quantities. And so that's a big thing. And we had a meeting with DARPA back in December, and this particular RFI, actually 2 RFIs we responded to in April this month, really were oriented towards components that go into the Razor and as a high Mach airplane.
Yep. Yeah, exactly. So what kind of temperature would you see on the Razor when it's at Mach 4 on the skin of that material?
Well, it really depends on your altitude and the density, but you're looking at around the 2,000 degree Fahrenheit range at times.
Wow.
It is quite hot. The main concern is the engine components. And so that's where the heat is really the most critical aspect, not so much the skin, because you have the leading edge skin temperatures, and then further down the skin of the airplane, the temperatures do differentiate. But the power plant, the intake, the combustion chamber, all of that, and that's really where we're getting our thermodynamic efficiencies. And so there's a lot of different tricks we're doing to have the air come in, compress it, have it come out, reduce signature, reduce exhaust gas emissions, reduce NOx, all of that. Instead of, it's kind of funny when you get into engines. Generally speaking, the higher the temperature differential, the more efficient. And so if you can get an engine to operate at a very high temperature, even upwards of plasma combustion type temperatures, you'll get very high efficiencies. But often the problem is you increase your NOx or something like that. And so balancing out how you do that is important. So that's kind of what that whole program is about.
So what kind of temperatures were you talking about then in the engine you'd see there?
The engine, that's really up to about 5,000 degrees in parts.
Wow. Was the SR-71 engine all built out of titanium, or because I know the whole other part of the plane was?
It had a lot of super alloys at the time. I think it had quite a bit of Inconel in it, and it was a high temperature engine.
Yeah, it's got a lot of nickel in it, doesn't it?
Lots of nickel super alloys at the time. So that was
cool.
A really neat engine. You learned a lot from it.
That's a neat plane altogether. And I love the story about how they bought titanium from the Russians to build a spy plane to spy on the Russians with it, right?
That's pretty wild. Yeah, they sure did.